Have you ever wondered how water silently travels beneath our feet, moving through silt and rock, shaping our underground landscapes? Well, understanding this hidden movement often begins with a fundamental calculation known as specific discharge, which we representing with the symbol lowercase q, the formula for specific discharge, or Q, is directly derived from Darcy's law and is expressed as Q equals K multiplied by I. This quantity, specific discharge, represents the volume of water flowing through a unit cross-sectional area of porous medium per unit time. This formula is central to hydrogeology because it is a direct application of Darcy's law, a foundational principle established by Henry Darcy in the 1850s. Darcy's law describes how fluids flow through porous media, such as aquifers. The formula works by combining two critical factors, K, which stands for hydraulic conductivity, and I, which represents the hydraulic gradient. Hydraulic conductivity, or K, quantifies how easily water can move through a particular material, considering factors like the size of the pores, their interconnectedness, and the fluid's viscosity. A high K value means water can flow quickly, like through gravel, while a low K value indicates slow movement, as in clay. The hydraulic gradient, or I, on the other hand, describes the change in hydraulic head, which is essentially the water's potential energy over a given distance. It tells us the slope or steepness of the water table or potentiometric surface, indicating the driving force behind the groundwater flow. To use this formula in practice, a hydrogeologist would first need to determine the hydraulic conductivity of the aquifer material. This often involves conducting field tests or laboratory analyses on soil or rock samples. Next, they would measure the hydraulic head at various points within the aquifer, typically using monitoring wells, to calculate the hydraulic gradient. Once these two values are known, multiplying them together yields the specific discharge, Q. This calculation helps quantify the rate at which water is moving through a section of the subsurface. An important nuance to remember is that while specific discharge, Q, gives us the volume of water per unit area per unit time, it is not the actual velocity at which individual water particles are moving. Because water must navigate around solid grains and through winding pore spaces, its true average linear velocity, sometimes called seepage velocity, is actually higher than the specific discharge. This distinction is crucial for accurately predicting contaminant transport or the time it takes for groundwater to reach a pumping well, which often requires dividing the specific discharge by the effective porosity of the medium. Ultimately, grasping the specific discharge formula provides you with a powerful tool for understanding the quantitative aspects of groundwater flow. It enables hydrogeologists and environmental scientists to predict how much water can be extracted from an aquifer, how fast contaminants might spread, and how changes in surface water bodies can impact subsurface water dynamics, all of which are vital for sustainable water resource management and environmental protection.
If you love learning about water, like, subscribe, and keep exploring with us.